Hi everyone, my name is Niaz Bisingulov and I'm going to present you ideas we've been working on at Michigan State University and EeroQ. The key object of this talk is electron on helium, and I'm going to do a quick introduction to this field. Electron located near the surface of liquid helium experience an attractive force towards the helium surface, but it cannot enter into the liquid helium due to high potential barrier. In this potential well perpendicular to the helium surface, electron energy becomes quantized. The energy spectrum of the electron looks very similar to the hydrogen atom, therefore these states called Rydberg states. At low temperatures, approximately a few kelvins and below, all electrons occupy only the ground state, therefore forming a two-dimensional electron system. Electrons on helium have many remarkable properties. One of them is the absence of the impurities and defects in the helium substrate, which results in a weakly coupling between electron and its environment. And due to this fact, it was predicted that the surface states of electrons will have long coherence times and can be used as a basis for qubit. The first realization, proposed by Plassman and Dickman, uses Rydberg states where qubit operation frequencies are in 100 GHz ranges. The second realization is to use a spin state. It was predicted that the spin states will have very long coherence times, reaching several seconds. Electron motion along the surface of liquid helium can be further localized by DC trap potentials, where we can have a lateral motional states with frequencies in a 5-10 GHz ranges. In this talk, I'm gonna focus on the chip architecture, which can utilize lateral motion states as well as Rydberg states. So the chip is a silicon wafer on which we can create a certain type of microstructures. For example, we can create long microchannels. If we take such kind of device and place near the helium surface, due to the capillary action, liquid helium fill these microstructures. Electrons can be generated from a tungsten filament which is located above the helium substrate, and electrons can easily land on the helium surface, creating a surface state electrons. Now we can create a set of long microchannels and use them as the electron reservoirs, where we can store electrons. We did experiment in such kind of devices, where two large reservoirs are connected with a smaller microchannel. In this experiment, we measured an electric current through the central microchannel connecting these two large reservoirs, and different voltages applied to the side gate and to the bottom gate. In these experiments, we identified three transport regimes: zero current regime, where the channel is closed; high current regime, which corresponds to the electron liquid; and low current regime, which corresponds to the Wigner solid state of the electron system. An interesting feature in this data is the fringing pattern which appears between two current regimes. This fringing pattern appears due to the formation of rows in the central microchannel. For example, in these experiments, we can identify from 1 up to 20 electron rows. These experiments demonstrate a good control over the electron system using such kind of microstructures. And now we can use these microchannels to bring electron to the trap area. The trap has a multiple control electrodes, and it is designed to have a specific type of electrostatic potential distribution. By choosing appropriate voltages on these electrons, one can create an oblong-shaped electrostatic trap, so electron is more likely to be oscillating along y direction. So in this case, this motional state can be coupled to the microwave electric field created from the RF electrode. The potentials calculated from the finite element modeling simulations we use to numerically solve Schrödinger equation. So here are results of these calculations. This is a spectrum of the motional states of electron, and these are four first wave functions. The anharmonicity of the trap can reach values of 100 MHz, which is comparable with superconducting transbonds. And in principle now we can use these two states as a basis of our charge qubit. These states can be manipulated with a microwave electric field created by a coplanar waveguide. We calculated these electric fields and estimated a coupling constant which reaches several megahertz. I should mention here a recent beautiful work which was done in Dave Schuster's group, where they coupled an electron, single electron, to a superconducting resonator. And they observed a coupling constant of 4.8 megahertz, very similar to the values which we calculated for our electron trap. Now let's talk about the decoherence. In this slide, I listed main decoherence mechanisms for the electron on liquid helium. The first, electron can decay with emitting two replons with opposite momentum. So these are quantized surface capillary waves. An electron orbital state can decay into a phonon inside the liquid helium via coupling to surface deformations or modulation of dielectric constant. The main source of dephasing is the voltage noise on the bias electrodes. With the numbers for decoherence rates presented on this slide, we can see that the coupling constant much larger than all of these numbers. So we are in a good shape here. Okay, now we want to use a radio frequency single electron transistor as a charge sensitive electrometer to measure charge qubit states, which will induce a different charge states on the SET. The readout of these charge states on the SET can be done by monitoring the damping of the high-frequency resonator to which SET is connected. Our plan here is to use on-chip planar inductor to make a tank circuit, and one needs to pay a careful attention to the capacitance to the ground. One of the results of this tank circuit simulation done by FEM is shown on this figure. We estimate the induced charge on SET from emotional states to be 0.2% of electron charge. Considering an optimistic values for SET sensitivity, which is limited by shot noise, we can estimate the measurement time of qubit states, which turns out to be 0.4 microseconds. During the measurement, the charge fluctuation on the SET can mix the qubit state, and we estimate the corresponding mixing time to be 1.2 microsecond. In principle, we satisfy the condition that we can do measurement before the mixing happens, but it will be very hard. The situation for Rydberg states looks much more promising. Therefore, we propose the measurement of the motional states via Rydberg states. It turns out that these states are coupled with a coupling strength approximately 0.5 gigahertz. Now let me introduce some preliminary data of our first SET device. This is the SEM image of the device we fabricated, and this is a measurement of the current, which show a pronounced Coulomb blockade oscillations. The noise on top of the signal is a telegraph noise, which indicates to a two-level fluctuator coupled to the SET device. This telegraph signal has a standard Lorentzian shape of power spectral density, from which we can extract information about the switching rates. These two-level fluctuators to be known as a problem in a number of superconducting qubit platforms, and it turns out that we can learn something interesting about these two-level fluctuators. In benchmarking of these first devices, we have submerged them into the liquid helium and studied how switching rates will change. We found no change in switching rates of the two-level fluctuators at low temperatures when we covered SET with the liquid helium. At high temperature, the switching rates go down in the presence of the liquid helium, which indicates to creating an additional energy relaxation channel into the liquid. The absence of this energy relaxation channel at low temperature can be explained by a Kapitsa thermal boundary resistance, which exists between liquid helium and the solid. So what do we do next? So our future plans is to make an RF SET and optimize its performance, and integrate this device into the electrons on helium experiments to do a single electron detection. In the end of my talk, I would like to thank our EeroQ team for constant support and also all members of LHQS group. Thank you.